methyl methacrylate, MMA, is toxic, but once you polymerize it or synthetically polymerize it to create PMMA, it becomes biocompatible. So first, PMMA was invented. Everybody knows it's called plexiglass, right? In the 1800s, but really first commercialized in 1928. They used it in World War II extensively, cockpits, all sorts of stuff. And that's when they first realized that, hey, if a plexiglass window shatters and it goes into the pilot's eye, that's actually less damage than glass. So they kind of knew some relationship between biocompatibility back then. So anyways, those are some very nice particles of PMMA. Those are actually microspheres, so they're specifically not for additive, but this was the best SEM picture of PMMA I could find. So PMMA, as I said, it's lightweight, high mechanical strength, shatter resistant, and it's an economic alternative to polycarbonate. And again, it's biologically compatible. So I'm going to talk about some applications. So it's been used widely, like I said, but I'm going to talk about specific applications to additive manufacturing. And so those include lost molds for investment casting. These are biological beads that surgeons can embed after they've done surgery to deliver medicine over time, and this will actually a body will reabsorb that material. And again, the porosity and the low absorption of the PMMA is actually what makes that very friendly for these type of applications. Here's a cranial implant that was recently designed and fabricated using additive manufacturing, which replaced a patient's skull. I'll talk about that a little bit later. This is the Aston Martin developed for Skyfall, the last Bond movie, and this was actually much cheaper to make and then blow up for special effects than the really expensive ones they used before. This was a backbone that was developed to study the methods of operating on spinal cords. And this is a prosthesis developed for amputees to be able to swim, and they can actually swim much faster. This was made using PMMA, architectural models, and actually this guy in Germany is building entire furniture sets out of PMMA. And you can have really cool looking furniture in your house. So there are a lot of things you can do with it. We've been doing a lot of stuff in the past, but now with additive manufacturing we can do a lot more. Here's some material properties. I actually had to go all through some literature and compile this myself, but as you can see, compared to conventionally manufactured plexiglass or PMMA, additive manufactured PMMA is not that great. But for the applications they're looking at, functional prototypes and biological applications, it actually performs well enough. So while I wouldn't, make a window out of it, I could still put it in my body, and I think that's a good takeaway from this. So one of the biggest vendors of this powder, Sigma Aldrich, all types of companies make PMMA powder, and we saw that in the first slide. But Voxeljet is a company founded in Augsburg, Germany. They're the largest manufacturer of machines, industrial size, and also the powder. So here are the typical characteristics of the particles they make. So that's particle size and the binder types they use. So primarily, actually only, they do binder jetting. And binder type B for some reason is only available in Europe. But a lot of these are used in casting and production of functional prototypes, as we see. So here is an example of some powder. So this is kind of what it looks like, what they'd be traditionally handling when they're making these models. So case study 1, Schmolz Bickenbach is a leading metal manufacturer, casting specialty company in Germany. Again, they use powder-based binder jetting to produce this Francis wheel. So it's an investment mold. It's a lost mold to produce FEAD brackets, powertrain components, gearboxes. Additive manufacturing really helped because they needed the molds to be detailed, precise. It really helps save time and cost in making these models. The strength was comparable to the wax models they were making first. What they do with these models is they'll make them and they'll dip them in wax, and then they'll put them in the kiln, burn out that mold, and actually, because the PMMA shrinks, it doesn't break that ceramic coating. So the mold is really, really good, as we'll see in the video on the next slide. So here's the process, and I'm gonna the company, and this is a different type of parts they've made. I'm gonna skip ahead to the actual printing process. So here, there's the binder jetting process. They're building up that investment lost mold for that Francis wheel. Let's see. Let's skip ahead to. All right. So she's removing the powder. Again, we've seen that before. And like I said, once that process is done, they're going to take it and they're going to dip it in wax. This essentially seals the mold. And for the molds they'll actually use to do the burning out, they'll actually infiltrate it with wax. So some of the prototypes they'll only coat, but the ones they'll use they'll infiltrate. And once they do that, let's skip ahead a little bit. So the manufacturer receives it like this. She'll inspect it, and then she'll start coating it in this ceramic support. And so they'll do it by hand at first, and then they'll do it by machine. And once they do that, like I said, they'll burn out that. So that's why it's called a lost model, right? So they burn out the model they built it initially. Then they're going to let it cool, and then they're going to pour some molten hot metal in there. And eventually, you get something that looks nice as this. And obviously, there's some post-processing involved. But as you can see, it's a very good application of additive manufacturing. Save lots of, like I said, here's the process. They're pulling metal in, post-processing, and you get the final part. All right. Next case study was by a company named Anatomics for the University Medical Center in Utrecht, Netherlands. They used, again, binder jetting process to, like I said, make this cranium replacement. There's a disease that goes among Dutch folks that your cranium, your skull grows too thick. It won't stop growing. And so if this continues to happen, you'll lose brain function. And they use additive manufacturing to replace her skull completely. And the advantage here, again, it's biocompatible. It was lightweight. Compared to the previous bone cement implants they used, the rate of brain function recovery was actually much faster. So, first instance of a successfully 3D printed cranium that had not been rejected by the patient. So that's really a big deal, right? We're able to put these in our bodies and improve the way we live, and I think that's very exciting. All right, so the first research study I really looked at was where they evaluated this binder jetting process. So they created this part, as you can see on the right, and they tried to evaluate it based on different process parameters. And so basically they asked, how do the mechanical properties compare to conventionally manufactured PMMA or plexiglass? I don't know if you can see very well, but as you can see, plexiglass outperforms most additively manufactured PMMA, but wax infills and epoxy, which is on the left there, really improve the properties overall. So as you can see, not as good as, to make windows out of, but something you could still use, strengthen. And wax actually gets you a better surface finish. So if you're looking for surface finish, wax is useful. So as you can see, the epoxy infill performed the best overall. The second study we're going to look at is FDM, where they actually did customized implants for the cranium. You can see the image. So that's the model they built out of ABS. And this is their porous implant. And this is the model with the implant on the skull, actually. And so they wanted to investigate the use of this. They wanted to see what the effect of tip wipe frequency and layer orientation would be on the mechanical properties. And importantly, porosity, because porosity is a key factor in muscle growth, in bone growth. It really helps biocompatibility of these implants. So what are the effects different fabrication conditions have on the mechanical properties? Porosity had a large impact. As you can see, the yield. So this is. They basically tested in the transverse and axial directions, and they found that the effects in the transverse direction were much better, and the effect of porosity was actually something that was advantageous when using an axial layer method. So these are my references.